So we'll consider a real problem is called fulfillment optimization. And this is an example it's called omni-channel. You have a different channel, and this is a physical store, and this is fulfillment center. So you have online and in-store customer. And right now we have 3 customer, and the reward or revenue is equal to retail price minus your shipping cost. So this customer at Washington DC from Los Angeles, and this is the reward, and this is the shipping cost, and this is the reward. Look at this nice review on Inform's tutorial in OR by 2 professors, and right now he works in, I remember it's at Amazon, and this is a professor at MIT. There are 3 solutions here, and because we have time limit, in case you are interested in this example, please look at the paper. There's 3 approach. The point is that one reward is 127, and one is 147. And if you could look into the future, the reward should be 176. And this one is 20% or 38% more than the previous one. And how could you look into the future? Let's use dynamic programming. And we won't cover the detail here, but the important message is that dynamic programming is an important tool to deal with a stochastic problem. And you could read this paper, and this is a professor at MIT, and this work is done while he was a PhD student at MIT, and won the MSOM. This is a top journal in published by Inform, and they won the Best Paper Award in this journal. And this is a real case study. They reduce the outbound shipping cost by 1%. And they do not mention which company. But if it is Amazon, we look at the scale, and this is the data for 2023 annual report. And this is the shipping cost for Amazon. So 1% is 1 billion, which is amazing, right? So my point is that why do we need learn this kind of difficult mathematics in school? Because when you try to deal with the real world, the real world problem is very difficult. And once you have a nice algorithm or toolbox to solve the problem, as you can see from here, its impact is tremendous. So we'll define the problem in terms of dynamic programming, and you will look at the paper for further detail because they use the other techniques, for example, optimization, and which we won't cover in our class. So the network, you have an I product and belongs to a bigger set, and you have a different node because you have so many fulfillment center. And T is time, so you discretize your time. And you assume order received at time T come with independent random variable to simplify the mathematical analysis process. That include the location of the order, service level, or for example, 1 day, or 2 day, or 7 day, different service level, and what are the order you order, and how many quantity. So the real problem is a continuous time, but to make the problem more easy to solve, we embedded a discrete time process. Okay, that is one technique. So this is decision, X sub Tij. T is time, I is product of inventory consumed from J, node J. So we need to satisfy some constraint, and this is the demand, right? So we need to satisfy the demand, And this is the stock we have. So we could not consume more than the stock we have. So this is an upper bound. And we have a reward function. So this is the problem. We try to maximize our profit. This is reward, one step reward. And this is cost goal. This is our current stock, right? And we minus X because we use it here. And we go one step further. So this is our current stock. We use it. So this is the next step. And we try to find the expected value because it's a stochastic process or random process. So there are several challenges to solve this problem. The first one is high dimensionality. We have, for example, for Amazon, we have over 200 nodes, and Walmart have 30. This is the information here. And for the Taiwan largest company, for e-commerce company, is called Momo, which have 59, and you have hundreds of thousands of products. So I and J are big, okay? And they are about the demand model. The other difficulty, it's a high dimensional problem, and some products have a low volume, so you have sparse data. So you still need to feed the data to find some parameter in your data model. And there are some seasonality in your product. Some item might popular in the weekend or during the in the United States at Christmas. In the Taiwan, I'm not sure in the Chinese New Year, or it's non-stationary. That is, it varying over time. And you have a different reward function structure. So we try to simplify the reward so that the problem is manageable. And so this is one structure, linear. This is the revenue times the quantity. But if there are some discount, as we mentioned earlier, it becomes a nonlinear, which is more difficult to solve. So the whole problem is very difficult, the real problem. So how could we reduce or find some optimal solution? And please look at the previous mentioned literature to look at some solution using optimization.